basically, I think you guys heard so many times what the gradient descent method, because I covered it under the topic of optimizations. But here the difference is I add a stochastic. So I'm going to explain what the stochastic gradient descent is and see what kind of the discrepancy in there. Okay, so we're gonna cover the gradient descent method and its variants. And so as you can see, all of them are gradient descent, but here we have a batch gradient descent, and another one is gonna be the stochastic gradient descent. Last one is gonna be mini batch. So I'm going to explain one by one, and at the end, we're gonna use mini batch gradient descent a lot. So there is so the batch gradient descent means I'm going to use the entire training data set for each iteration. Stochastic means I'm going to randomly pick one of the training data set, and mini batch is kind of between. So I'm going to explain what these things, and I'm going to explore the concept of these three different gradient descent methods. So, for instance, I'm going to use the logistic regression models as examples to explain it. And last topic is going to be, there's some limitations on the gradient descent. So I'm going to explain or discuss what will be the limitations of that. And there's the smarter way we can overcome some of the limitations. Here, there are so many, but I pick one of them. It's going to be adaptive things. So I'm going to discuss or explain what it is. So let's talk about batch gradient descent first. Here, the batch gradient descent is same as gradient descent that we already learned from the optimizations. So as you can see, I mean, this is so important. And assume that we are in say, let's say n-dimensional space. So it will be in multivariate. So again, the omega is here is not a scalar in general. It will be the column vectors because we are dealing with multivariate space. And as you can see, we can define, I mean, the objective functions. Objective function it's a scalar, but since we have many different elements in omega column vectors, we have to compute the gradient of function of f. So here in the gradient, what the gradient descent means is we're going to repeat and we're going to keep updating the omegas, starting from the omegas, and compute the gradient, which means here is the directions, the slope, and in the opposite directions with alpha, and here is it's a step size, or you can think of as a learning rate. And then there will be the updated omegas, and we're going to repeat the process until it converts the promising values. That's a gradient descent. I mean, I explained so many times, so I'm pretty sure that at this moment you guys are familiar with these things. And here, this one is the graphical illustrations in 2D. See, in these the contours of objective functions. This means these are the same, the values are the same. And as you can see, say we starting from here, then if we compute this, it will be the normal vector and the increase in the positive slope. since we have minus, it will be the opposite, and we have the multiplied by the step size alpha. So it's like that. And here, next step probably, let's say we are here, and it's updated and repeated that process until it reaches hoping that is hoping the local limit minima. Right? Make sure you understand why these are the 90 degrees. That's the definition of the gradient. I mean, the gradient in the multivariate case. And let's see the equations. So again, still it's a batch gradient. And suppose, I mean, we use f as objective functions. But here we often use the loss functions. I mean, these are the same, but if you set the objective function as loss functions, because we are already trying to minimize things. So it's we want to minimize the loss functions. Basically, these two functions are the same, it's different name. What I want to do, say this one is true labels or true to the value of outputs, and this one is the estimated, mated, or predicted the label, all the values, all outputs, output. I mean, usually it's for the regression problems. I rather say it's outputs. For the classification problems, probably it's label is more natural way to say. And each data point, we can compute the loss functions. Loss function is any kind of functions that the user can define, right? In common the sense in the regression is probably the least square, and for the classification it will be the cross entropic things. And for I want to, because we have m, suppose we have n training data set. That's the entire data set. So I'm gonna do the summations for compute loss over all of the training examples, and these are just divided by 1 over m. It's just the mean. Summations and means are the same, pretty much the same. And there will be the definition of loss functions. Now I want to do, because this will be the objective functions, right? And in order to utilize the gradient descent, I have to compute the gradient. So basically, I want to compute the gradient like that. And we know that, say, this is the functions, and these are the loss functions. And the good thing is that the summation it's a linear gradient, and the summations, both of them are linear operations, so we can swap it. So here I can swap these things, and what I'm saying is that we compute the loss functions and do summations, and then at the end we take the gradient. But here what we did is we did gradient computation first and then do summations. So what I can say is that I can compute the gradient for each but entire training data set, and later on we do summations. That's how we compute it. So here we do maybe I will say gradient or partial derivatives, and then do summations over entire training data points. So when you think about the computing process, so each iterations you have to to these computations. So that means computing the gradient requires summing over all of the training examples. And we're gonna say this is batch gradient or batch training. The problem is that the batch training is in real life, it's impractical because especially when you have say like millions of training examples, you have to do a lot of computations. The worst thing is this one is for the single iterations. Right. So what I'm saying is that in the gradient descent we have loop and iterations. For each iterations, you have to compute the loss functions for the entire data set, and we have to take the partial derivative for the entire training data set. That requires lots of tons of the computations. That's the big limitations. And on the other hand, now here it's kind of in the totally opposite directions. You have a batch gradient descent, and on the extreme opposite side, there's a stochastic gradient descent. So, think about it. Say, let me see. The idea is that I want to update the parameters omega based on the gradient for a randomly selected single training example. It means that each iterations instead of doing summations for over the entire training data set, I'm just gonna randomly pick one of the training data set. I will do one gradient computation. Okay, so here, let me see, these ith is randomly selected. So the key thing is a single training data set. Right? You see that the batch for the entire data set, the stochastic gradient descent is just randomly selected single training data point. That's the big difference. And this one is a good illustrations that you guys can see the difference. And the blue is, as you can see, it's a batch. And the red one is a stochastic gradient. Since it has a lot of randomness, and as you can see, sometimes if I pick the right data points, probably here is kind of okay, but sometimes if you do not have a luck, probably this data points is like kind of going that way and the other way like that. So stochastic gradient take a step in the noise directions. There's a lot of uncertainties and randomness on it. But the good thing is, it's gonna move downhill on average. You guys, so that's the key things. During the iteration process, sometimes if you do not have, if it's not fortunate enough, probably the points is gonna move in the noisy directions, but in general or over on average, it's gonna move downhill. That's the way. So during iterations, it might be noisy, but eventually it will move down to local minimum. That's what we want to believe, right? And the mathematical justifications, you guys don't have to understand, but if you sample training example at random, the stochastic gradient is unbiased estimate of the batch gradient. I mean, here is you don't need to do not need to fully understand, but I mean, here is for these are the expectation is same as the sample means. This is expectations, and these are the sample means. There's kind of mathematical justifications, but it's okay. I mean, again, so to summarize things, there are two extreme cases. One is the batch gradient, the other one is the stochastic gradient. Stochastic is because the one of, I mean, batch gradient is the best if you can do, but you can see that if you have a big data set, each iterations, it's going to require a lot of computations. So we don't want to do that. So in the opposite extreme cases that it's a stochastic gradient is I'm going to use randomly pick one of them, right? But it's very noisy on it. And I hope that you guys can see the big difference that these two different gradient descent methods. Okay, so here is the title is stochastic gradient is sometimes better. What do you mean by the sometimes better? Let's think about this. So if we have here, I said it's the full batch gradient. If we do batch gradient descent, if you suppose you're starting from here, then we'll do gradient update. And it will be the batch gradient descent solutions, and it's end up being the local minima. But on the other hand, if you think about the stochastic gradient, I mean, here is sometimes, but each iterations, it really depends on how you, the data points that is randomly selected. So in some case, you have, it's, say you have, I would say, how I say, in probably, in here, in some case, you have larger value of the gradient, then you might have a chance to jump like that. So in noise way, probably I would say noise stochastic gradient can help occasionally escape the local minima, but it does not guarantee that this is what is going to happen always. I say. So there's pros and cons for the stochastic gradient, and I hope that you can understand intuitively. So any questions so far before I move to the mini batch gradient descent that no?
Nope.
Okay, so this is the mini batch. So this is the final things that I believe that we're gonna use a lot, very often in the actual implementations. So potential problem of stochastic gradient descent is very noisy, as I just mentioned in the previous slide. So here, I will say for the stochastic gradient descent here, batch gradient descent. Say we have, suppose we have m trained data points, right? So here is entire, and here is just single data points. And I mean, in order to compromise this, probably I will say I will just pick the value in the middle, right? I guess this is kind of educated guess or reasonable guess that you guys can think of. So the compromise approach is that we're gonna compute the gradient in a median size of medium-sized set of trainings like that. So we call it mini batch. Again, the S is user-defined, which means if I program it, I can decide. S can be like, I don't know, maybe 10 or 50 or 100. It really depends on us. But hoping that the value is smaller than the entire data set. Okay? So that's something that user-defined. We call it, this is hyperparameters. Okay, let me see. So this one looks like exactly same as the mini batch. I mean, same as the batch gradient descent, except this, the batch size. So it will be probably, I will say this one is batch size S. And the stochastic gradient compute, I mean, if you increase the batch size, probably you will have the smaller variance. I mean, this is it's very intuitive. And the mini batch size is S is the hyperparameters that you need to set. So that's what. Okay. I mean, I guess it's kind of the compromised approach, and I think to overcome the weakness of drawback of stochastic gradient and batch gradient descent method. And let's implement this and to see if what kind of effect that you can observe. So I'm gonna use I mean, logistic regressions that you already I discussed in the previous lectures, and I'm here. I'm gonna make comparison on the 3 different gradient descent algorithms using these data set. I'm hoping that there will be linear boundaries eventually. And let's think about gradient descent. I mean, just look at the titles. Here is a stochastic and with the mini batch. All right. So let's in here just looking at this side first before we just take a look at how we implement it here. So look for the batch gradient. I mean, this is the finer linear boundaries, and this one is, and this one. As you can see, I mean, these are 3 different methods give us the pretty much the similar or pretty much the same the linear classification boundaries. And here, let's look at as we increase the number of the iterations, just look at the loss. And here is probably, I would say, nice and smooth for the batch gradient, because here I'm not sure how many data points here I'm not sure, but suppose we have, I don't know, maybe it's like 1,000 or 10,000, and because we select all the training data set and we take the average of them, so as you can see, very smooth. But on the other hand, for the stochastic gradient here, I hope now you kind of see or understand why we have this kind of the loss graph, because each iterations, a lot of noisy things happening, because we took the stochastic one. And the mini batch is like, I mean, still you can see a lot of noise things, but in general trend is like, okay. So that's the comparison that I can make. And let's take a look at here. So for the batch gradient, let me see. Let me see here. For the X and Y, we define the placeholders for the inputs and the outputs, and the placeholder size is same as the size of training data set. So here M is size of entire training data set. And these are the TF variables, and here it's a two-dimensional space, including the constant. We have the omegas, and this is how we define the loss functions, and this is binary classification problem. So the only thing that you have is sigmoid cross entropy with the logits, and since this is multiple data points, we have to take the reduced mean. And I use the gradient descent optimizers with the running rate, minimize that loss functions, and we initialize it. And then let me see. Now here, and each iterations or optimization process, I'm gonna put the entire training data set into the placeholders of input X and output Y. Okay, that's the typical way of how implementing in the batch gradient descent. And on the other hand, for the stochastic one, let's see here. I mean, okay, this one is batch and this one is stochastic. As you can see in the structure wise, that's pretty much the same. But let's take a look here. And for the placeholders, this is one training data point, right? It's not M. And let me see here, X and Y, it's placeholders, and I'm gonna feed it in the batch of X and batch of Y. Here, how we define the batch, I just, among the entire training data set, I randomly pick only one. That's how we implement it, the stochastic gradient descent. For the mini batch, here I have mini batch size is 50. It's a hyperparameters that I can choose. So in this case, I don't know, but there's no specific reasons, but I pick 50. Right? You can try like a 10 or 100, whatever. So that's the batch size and here these are pretty much the same. And just here for use a random dot choice, and the size is same as batch size, and I pick here 50 of them, and I plug in that into the placeholders to implement the mini batch gradient descent for the logistic regressions. Okay, so I explain what the the batch gradient and stochastic and mini batch gradient, and implement it, because we learned the logistic regressions and we learn how to implement the logistic regressions in the TensorFlow. So that's why I just take that as another examples to explain it. There is the differences of the famous gradient descent method. You guys, hope that this is very clear. Good?
Yes.
Okay. So let's move on to the limitations. I mean, the gradient descent I explained is looking good so far, but again, I mean, there's some limitations, and let's see. Setting up the running rate, which is alpha. The question is, this one is another hyper parameters that I need to decide. That's the so how the thing is, how can we set the running rate alpha? I mean here, I mean we learned that it's if we have a smaller value of alpha, it's gonna converge slowly, and sometimes it gets stuck in the local minima. And on the other hand, if you have larger value of alphas, probably it's gonna overshoot. And in that sometimes it will be unstable, and even worse, it will be is diverse. So that's kind of general explanation of how the value of running, I mean the running rate or alpha can affect the gradient descent iterations and the process. And there are some two suggestions to overcome this. The first idea is try lots of different alphas, see what kind of value work just right. That's basically it's trial and errors. Basically, like spend some times and run it with different value of alphas, right? I mean that's I mean very I mean looks I mean it sounds like the it's not attractive, but it's very efficient in many cases. A lot of people do these trial and errors to pick the just right values for alphas. The second ideas or suggestions or approaches is a bit smarter, and we want to design the idea is adaptive. Instead of having constant value of alphas, we're gonna change the values of alphas. We call it adaptive. So there are two. The meaning of adaptive here is a temporal or spatial. This one is I mean over iterations. I mean in time wise, and we can change the value of alphas over iterations. Or here it's in the spatial thing space. What I'm going to explain what this means in the next slide. Let's think about the alpha step size. And the gradient descent methods make strong assumption that it's assumption about the magnitude of local curvature to fix the step size. It's isotropic, so the same step size makes sense all the directions. I mean, this sounds very complicated. Let's think about this. I mean, here is the isotropic is. So what I want to explain here is I want to say here. So explain it here. Let's think about here is in two-dimensional space. I have, let me see. Here is omega 1 and omega 2. Then let me see. Here, so if we have the data points here, probably this is the direction for the gradient, the, how do I say, loss functions. And we go the opposite directions. But since we do, how do I say, let's think about that. So in the vectorized means have alphas, and probably I will say okay, right? So in the omega 1 we will do here we can observe that is we're gonna use same value of alpha for the omega-1 directions and omega-2 directions. So it doesn't matter what. So let me see. So probably I will move here. This one is better to explain it. Let's think about here. Suppose we are here. I mean, let me see. I mean, this will be minus of gradient. And in this case, it's if you have same alphas, all the features are equally important. That means here, how do I say, gradient these values are pretty much similar because it's isotropic. Okay, so let me explain these things this way. Here, if I compute it at this point, what will be the value of this one? How do I say? I want you guys to understand this, but so let me ask. In these directions, these are the equal values of loss functions, right? So it's a contour. So if you walk in this way, do you think about the slope? And if you walk in these directions, and let me ask, which one is steeper? Which one do you guys think is steeper? Think about the slope.
First one, maybe.
It's a contour. Think about the map. In the map, you have is if you have that kind of the contour on your map, say it represent the mount, and which way is more steeper? Probably I'm gonna write it in 3-dimensional way. Let me see. This one is kind of like that way, and like this way. Do you guys know what I'm trying to do? Let me write it again. So this one is to contour things. Say, I'm gonna say like that. This way. Is it better to visualize in 3-dimensional space or no?
Yes.
So this way is much steeper than this way, right?
Yeah.
So if you compute the gradient in that directions, it will be, say it's loss functions, say it's omega-1, and in that directions is which one is going to give us the larger value of m? I mean the magnitude. Don't worry about the directions.
The steeper one.
So, right?
Yeah.
And I'm gonna add the same value of alpha. So this means if I do update, since we know that this one is the bigger than this guy, so I'm gonna update omega 2 more than omega 1. Because we have, do you guys know what I'm talking? So this one is kind of like, this one is like larger value of alphas, and this one is a small value of alphas. It's acting like that, although we have the same value of alpha, because the gradient are different. You see what I'm doing it? So let's think about suppose we have, and this is the same as alpha. And if we have alpha is like, this one is, then in that case, this is, how do I say, this one is, it's isotropic. So it's pretty much the direction does not matter. So it's going to walk this way throughout the gradient descent update. And this one, as you can see, in these directions we have, it's very, let's see, I'm gonna say, two, most function is, and there's directions. I mean, this is smaller and this one is big. So even though we have the same alphas, the updating rate, see, how do I say, you starting from here in omega 2 directions, we updated a lot, but in omega 1 directions, it's updating very small. You see what the figure tells us? So
Yes.
okay, so what we can do is let's increase the alphas, because this way I think this one is good enough, and this one is not updating very often. I mean with the proper value of the size of gradient. So I can increase the alphas. Let's increase it. So I increase, I mean 0.02, and here maybe like 3 steps it converts to in these directions. But since we have larger value that it's getting, we want to reach at this point, but it's almost, as you can see in the previous one, and the previous one was here, and then like it goes further, and let's keep increasing it. So it's like 0.04. So in these directions, I mean, it looks okay. But in this direction, it start overshooting. You see that? Let's keep increasing it. And you can see the clear behaviors in these 2 directions. I mean, if we keep increasing it, like now it's diverse in these directions. I mean, this way is still it's approaching that in the optimal points that we want to that expected, but in that directions, it's unstable. That's the one of the problems of having constant value of running rate or alpha or step size in the spatial mean. And let's switch the topics in the temporal way. So this means this one is like over time. With the constant values, constant alphas, we does not change the value of alphas over iterations. But typical strategies use larger alpha early in a training so we can get close to the optimals. And gradually we decrease or decaying the value of alphas to reduce the fluctuations. Does it make sense? So when you do iterations or training at the early stage, a lot of we pick the initial point is randomly, right? So it's a lot of uncertainties. In that case, I want to jump around. So typically we pick the larger value of alphas to kind of intentionally get some noisy directions. And throughout the iterations, I want to gradually decrease the alphas so we can reduce the effect of fluctuations, and eventually hoping that it converts to the optimal solutions that we want. That's the typical way of overcome the temporal issues on having the constant value of running rate. Does it make sense so far?
Yes.
Okay, so this will be, so it will be almost the last one. And here I will call it adaptive running rate. And let me see, stochastic gradient. I'm using constant, I mean, here is eta is same as alpha. Sorry for the using different notations, but suppose this is a constant running rate for all iterations and all directions. I'm talking about temporal and spatial things at the same time. And there's some other method is add other, I don't know how I other grad things. And this is the rule for update. So this one is, let me see. Don't worry about these epsilon things, don't worry about it. This one is sum of squares of a gradient. Let me see, how do I say? Let me read this, let me erase this. And suppose we have this one is like gradient theta ith of those functions at time t, and this one is sum of squares. So since I have, it will be this one will be 1 square things like that. So this one, the value is gonna be gets larger as I increase. because we do summations. Then this one is, I mean, like that, right? So it gets the value gets smaller. So these are kind of adaptive running rate, right? So this one, the values get smaller as we increase number of iterations. Does it make sense? And let me see. And another in this kind of thing that how we set up the adaptive running rates over temporal way, and the special things here. I want to have. Let me go back to for smaller here in that case. In omega 1 is for the small value of gradient, I want to increase alphas. Right? For larger value of gradient, I want to reduce the alphas. So if we have larger, if we have a smaller gradient, I want to increase alphas. That's the first thing. For larger gradient, I want to decrease alphas. So if we move to see the adaptive ones, I mean, these are the gradient. And this one is sum over squared. So if we have a larger value of a gradient, this will be the large values, and this is 1 over squared, so it will be smaller alphas. You see that? So this one is, it's small, perform smaller update, and this one is perform the larger update and things. So deep learning usually rely on the smarter use of gradient using statistically over its past value to make the smarter step with the current one. So let me summarize. I mean, I don't think I explained where for the adaptive running rate alphas, but there are many different ways that we can set or we can pick the value of running rate or alphas. A smarter way will be the adaptive way. And this one is one of the examples that the people that developed. The good thing is that you don't have to worry about it because a lot of different optimization schemes or methods are already embedded or implemented in the TensorFlow. So you just all you need to is know what kind of the different method is exists and use that when you just use that functions in TensorFlow. So I mean that will be this one will be the last one. There are many different ways, momentums and eta grad and atoms and RMS power, whatever, and these are implemented. Right? So all of them are adaptive for smarter setting of alphas. That's all you need to know or understand. So probably most likely we're gonna use atom optimizer a lot in these lectures, but you don't have to stick to atoms. But think of, I mean, this is for the atoms optimizers. I mean, you just think of that's one of the adaptive optimization method, and just dealing with adaptive running rate alphas. And if you want to know for the advanced runners, want to more additional details, probably just go on this website to see the detailed explanation for different method for the adaptive